Hello, everybody, and thank you so much for inviting me to this workshop. Thank you mainly to Professor Ling Shou for this invitation. So my talk today will be about Markovian and non-Markovian models and the comparison between the results of these two types of models. So the results that I'm going to present are part of a manuscript that has been published in archive. The preprint are available in archive, and this work is work of Chi-Wei Yang, Joan Saldana, and myself. And the title of the work is Generalized SIRVS model incorporating non-Markovian infection processes and waning immunity. So the paper is currently under review for publication on a journal. And so what we have done in this paper is to develop a model that incorporates a non-Markovian infection process based on generation times, and I will explain everything about this, that follows a Weibull distribution. And then with this model, we focus on two points. One, compute the critical vaccination rate needed to achieve herd immunity, the disease-free equilibrium. And second, study the dynamical behavior of the model with partial differential equations and with an agent-based model approach. And so the motivation for this work is mostly one motivation, which says that the empirical, so based on measurement, compartmental sojourn times are often shown to be non-exponential. And so, since Markovian models instead are based on exponential compartmental sojourn times, all the modeling based on Markovian assumptions cannot be used. So, based on this empirical determination of these sojourn times. And so this non-exponential distribution implies that we need to use partial differential equations to take into account these non-exponential distributions. And these partial differential equations are kind of complicated. I'll show one. It is possible to simplify them through a stage progression models where each compartment, for example, the infected compartment, is divided into a series of Markovian compartments, like the infected compartment will become infected 1, infected 2, infected 3, infected 4. Each of these will have an exponential sojourn time, but all together they can approximate the needed empirical distribution. However, even under this approximation, this non-Markovian model definitely introduces complexity. So the question is the following. We understand that these models are more realistic, but they are also more complex. Are these more complex models really needed? And so our hypothesis that we develop in the presentation is that it depends on the specific goal. For example, to find the critical vaccination rate for herd immunity in a specific COVID type epidemic, which is the one I'm going to explain, these non-Markovian models are not needed, so we can simplify things. Okay, so summarizing and anticipating the results of this work, we can say that under the constraint that we have the same value for R0, we observe two things. One, that Markovian and non-Markovian model have big differences in the transient phase. So if we need to use non-Markovian, if the empirical information is non-Markovian, we need to use non-Markovian model. We cannot simplify using Markovian ones. However, the critical vaccination rate needed to achieve herd immunity is the same between non-Markovian and Markovian models, as long as the mean duration of the immunity period is the same. So in that case, we can avoid to complicate our life with non-Markovian models. So the conclusion in this case is that the additional complexity of non-Markovian infection process is not needed when computing the critical vaccination rate. And we think this is an interesting result. So let me give you some of the definitions that are used in the following. First, and very important because our work is based on this, is the generation time. So generation time is the time between the infection of a secondary case and the infection of the corresponding primary case. So an individual gets infected at this time, and then this generation time is the time spent before the first secondary infection due to this individual is created. And then we have age of infection tau, which is the time passed since one individual has been infected. And we have also, in general, age in each of these compartments. So, for example, we have age of recovery, we have age of vaccination. So the time that an individual has been spending within a given compartment. Then we have the probability density function of the generation time, W tau. So obviously, if this is a probability density function, W tau time epsilon can be seen is the probability to produce a secondary infection at the age of infection tau, tau plus epsilon. Okay, so it's a probability density function for the production of a secondary infection. And then we have gamma, the recovery rate, also being function of the age of infection tau. We have the per contact infectiousness beta tau, also function of the age of infection. And then we have the contact rate C, which is the number of contacts per individual in a randomly mixed population. And so we can summarize a well-known result in terms concerning the definition of R naught in the case of age of infection. And so this is the expression R naught is the sum of the infections caused by an infected individual at each age of infection. So it requires the integral between 0 to infinity of beta tau in the tau, where tau, we said, is the age of infection, and beta tau is the infectiousness times the number of contacts, because this infectiousness, as you remember, is per contact. So we need to multiply times the number of contacts. And so this is the expression for R naught, and this exponential value is the conditioning on the probability of that individual to stay infected. So it's the sum of infection caused by an infected individual at each age of infection in a totally susceptible population, conditioning on the probability of being infectious at each state. And this is this survival probability, meaning surviving into the infected state. And so this is the value of R naught, and from this, a very critical result concerning our work is the generation time probability density function. So a result from Waning and Lipschitz in 2007 says that during the initial phase of an epidemic, this generation time distribution W tau can be written as C beta tau, the infectiousness profile, exponential of minus integral 0 tau gamma S in the S divided R naught. And so this is the critical point because shows how this W tau, the generation time distribution, is related to beta tau. And so when you change one, you change also the other through this relationship. And so what happens, very importantly, is this one, that from an empirical determination of the generation time distribution W tau, so when we have cases like COVID where you measure this distribution of the generation time W tau, from this one, we can deduce beta tau, the infectiousness profile, and use this infectiousness profile within our simulations. And so the study of non-Markovian infection processes can be based on the distribution of the generation time times during the epidemic spread. And so the model that we have considered is the following, with 4 compartments: susceptible, infected, recovered, and vaccinated. And so obviously the population is initially in the susceptible state, and with the contact with infected, it will transition with a transition rate of C beta tau. So in this case, a function of the infectiousness, which is a function of the age of infection, and then stay infected for some time and transitioning to the recovered and immune through a transition rate gamma. When being in R, the individual is immune, but this immunity will fade out approximately after some time. For example, in our model, in our simulations will be 6 months, and then the individual will transition back to susceptible because it's not anymore immune with a transition rate delta. However, we have also vaccination. Both susceptible and recovered individual can be vaccinated with a rate V, the same rate. Once vaccinated, also the individual is immune and stays immune for, again, a given amount of time, on average, for example, in our COVID type model, 6 months, and then will transition out to S, susceptible, when this immunity wane out. Okay, so this is the model that we are considering. And it's important to consider that why S is the stays for the population density as a function of time only. All the others, for example, I, R, and V, are in our model the population density in the infected compartment at time T and sojourn time tau. So they all depend on tau. So I of T tau, R of T tau, V of T tau. And this sojourn time obviously are different in the different compartments, but we don't call differently for having a lighter notation. And so the model equation with these partial differential equations becomes the following. The important thing to consider now is that there is another variable in addition to T, which is the normal variable of the ODE, which is tau, the age of permanence in that compartment. And so we have the first relationship that says that the sum of the population remain constant under our assumption. We don't have demography. And then the equation governing the dynamics of the SIRVS model are the following, with the partial derivatives and considering on the other side of the expression the output flows in the transition diagram. For S, instead, as I said, the susceptible population does not depend on tau, so the derivative is only for t, and this derivative depends on the force of infection and the amount of flow going out of the S compartment because of vaccinated process. And the input to this compartment are instead the vaccinated and the recovered that lose immunity, so will go back to S. So this symbol phi that multiply S, which is the force of infection, is given by the following expression: phi of t is equal to C beta tau, the integral between 0 and infinity of beta tau I tau of n over n in the tau. So it's the usual expression, but we need to put the integral to consider all the possible age of infections. Additionally, we have boundary conditions at tau equals 0 and initial conditions at t equals 0. And so this is kind of a heavier set of equations when we compare what we obtained if all the rates are constant, if those rates gamma, beta do not depend on the age of infection, on the age of permanence. And if the rates are constant, we obtain the ODE model that was presented by Anderson and al. In 2020 concerning COVID. And so in this case also for this model, two equilibria are found: the disease-free equilibrium and the unique endemic equilibrium, with this number of susceptible in the endemic equilibrium being the usual n over R naught value as in the SIS model. For the disease-free equilibrium instead, the first one, we have the situation where we don't have any infected, we don't have recovered. However, we have a portion of the population being in the susceptible state and another portion being in the vaccinated state. So the disease-free equilibrium requires an amount of individual being in the vaccinated state. And so from these, we can consider that the force of infection at the endemic equilibrium is given by this expression 3. And when we impose for the bifurcation that the numerator is equal to 0, we have that the critical vaccination rate can be written as R naught minus 1 divided tau bar dV. And so it's important to understand here that this critical vaccination depends on the mean immunity period of vaccinated individuals only, not the distribution. So this is why we said at the beginning that if we want to compute the critical vaccination rate, we don't need a Markovian model, because this expression, at least theoretically, but we checked also the results of the simulation, does not depend on the distribution of the immunity period, but only on its mean value. So it's going to be R naught minus 1 divided this mean immunity period of vaccinated individuals. And so in order to check this model, we used an agent-based model, which gives us stochastic results from behavior of agents. We use 500 simulations for each scenario. We put R naught equal 2.5 and kept this value constant throughout all the simulations. The contact rate was assumed to be 10. And we assumed also that recovered and vaccinated individuals have a perfect protection, and the mean immunity period was of 6 months. So we were inspired for this type of assumption by the COVID type epidemic. And so the general setup for the ABM is that it was implemented through a software called AnyLogic 8. We also had results from solving the partial differential equation model, numerically integrated by using finite differences scheme. We made the assumption, and we used as our input a generation time distribution that was following a Weibull distribution with variable mean 4, 5, 6, 7, and 8. We consider two values for the mean infectious period, either 14 or 7 and 7 days both, but I'm going to present the results for 14 days. And we had the rate of immunity loss equal to this value 0.0055, which is corresponding to an average duration of 6 months. And for these values of R0 and delta V, the corresponding critical vaccination rate was calculated equal to this number. And so the first thing that we did was to double check our assumption about the relationship between W tau, the distribution of the generation time, and the infectiousness profile beta tau. So what we did, we defined several curves, these red curves that are on top here, and they are the theoretical generation times that follow a Weibull distribution with different parameters. And then from this Weibull distribution, this theoretical generation time, we derived the value of the infectiousness profile. From that infectiousness profile, we implemented the model, and we computed the distribution of the generation time. And what happens is that the computed distribution follows perfectly the theoretical generation time. So this is a very interesting and useful method if we want to simulate a non-Markovian model, and we have as an input the W tau, the generation time distribution. We can go from that to beta tau, which is the infectiousness profile, and from that, using that for our simulations. And so first we see the impact of vaccination. So these are multiple curves. We have time in the x-axis and fraction of infected in the y-axis. And these two situations, the panel A and panel B, report two different values of the vaccination rate. In panel B, we have that the vaccination rate is exactly equal to the critical vaccination rate. And we can see that not only for constant infectiousness, which is the Markovian model, but also for varying infectiousness, which is the non-Markovian set of models. At the end, when times increases, we have a zero number of a fraction of infected. So after first peak, then because of the vaccination, the epidemic will die out. If we have instead a vaccination rate equal to 0.5, after the first peak, there will be other peaks, and the steady state value at which all curves converge is going to be different from zero, a non-zero value, a positive value, clearly. And as we can see, all the curves here converge to a unique value. So this is what we were saying. We don't need the Markovian model here, because also the black curve was enough to give us this prediction. And so this is the first case, impact of vaccination, when we start with a population which is fully susceptible. We add a few infected individuals, and we start the process of the spreading and the process of vaccination. This is what happens. However, we did another another trial when we assumed that instead, at the beginning, the population is in part susceptible, but in part is also vaccinated, considering that we are at the disease-free equilibrium with vaccinated and susceptible. And we were trying to see what happens if we insert a new infected individual in this population. And so we did this with the ABM model. And we saw that when the critical vaccination, the vaccination rate is equal to the critical vaccination rate, we don't have an epidemic because we have a few cases at the beginning, but then the value goes to 0. And here, these few cases you can see is because the fraction of the infected is 1 times 10 to the -4. So it's a very minimal size epidemic that is visible only because we are using an ABM model. So we have this stochasticity effect that, for example, if we run the PDE in this situation, these curves will be all zeros all the time. However, in the same situation, if we use half of the critical vaccination rate, 0.5 VC, we see that we have a non-negligible epidemic going up to 0.1, a little bit less, a fraction of infected, and converging to also a non-negligible number of infected individuals. And so this is kind of confirming the same thing. All the curves here converge to the same value. So the non-Markovian, the Markovian model is good enough to represent this value of tendency here and here. Okay, so let's see instead the other interesting aspect, which is the transient behavior. So we have here the case of a transient behavior for the epidemic in time, where we report the fraction of infected cases, fraction of recovered cases, fraction of susceptible cases in time through the ABM model. And here in the first panel, instead, we compare the value of the PDE result for the 3 compartment S, I, and R. And so these are the dotted curves, and compare this with the median of the results of the ABM. And we can see here that the agreement is almost perfect. So the 2 models are well supported. So the ABM supports very well the results of the PDE. And then we see in terms of the fraction of infected cases that we have this behavior with a primary peak and a secondary much smaller peak, but not a lot of distribution. So all the curves are more or less very, very similar in the case of Markovian model. So we are looking at the Markovian. If we go to the non-Markovian, the result is different. See, okay, this is the difference. As you can see here, even though also in this case, the PDE and the median of the ABM, they are in perfect agreement. Here we see much more oscillations. We see a much bigger variation. If you go back, you see these curves, they are all overlapping one on top of the other. Here they are not. The secondary are much more big in terms of amplitude. And we see another very interesting phenomenon that we don't see in this one here. Look at this point. In this case, we have some simulations that after a first peak die out. So we have this phenomenon that some of the runs of the ABM simulations will not produce a secondary peak, but the majority in this case will produce a secondary peak. So we wanted to understand more this point. And we computed the risk of secondary wave occurrence in non-Markovian models. And so in this case, we have this graph where we have this blue color to show the percentage of simulation runs given a first epidemic peak with secondary epidemic wave. And so we can see that for mean generation time of 8 and large population like 100,000, 500,000, we have 100% of the runs having a secondary epidemic wave. However, when we go instead on the other side for small mean generation time and relatively small population, 20,000, we have that only 1% of the curve will have the secondary peak, but 99% of the curves will instead die out. And so we thought this was an interesting aspect shown by the non-Markovian models that was not shown at all in the Markovian one. So this is really a point of a big difference between the two models. And we wanted to understand a little bit why this was happening. And maybe we have a sort of explanation looking at this dynamical behavior of varying infectiousness curves for different mean generation time from 4 to 8, and the constant infectiousness, which is the Markovian. So if we look at the Markovian curve after the first peak, we see that the epidemic reduces the number of fraction, the fraction of infected is reduced, but it doesn't go really close to 0 as the non-Markovian, so stays a little bit higher than that. And this is maybe the reason why in this case we don't have any die out, because still the number of infected maintains clearly greater than 0, and that brings to the second wave. Instead, and so this can be one reason for to motivate why in the Markovian we don't have any die out after the first peak, but we have a die out in the case of the non-Markovian, because all these curves instead they go much closer, they approximate 0 much more, as you see here. So approximating 0 on the stochastic side, when this fraction is very, very small, at that point, it can happen that the epidemic will die out after the first peak. And so we have this phenomenon that it goes to 0, the epidemic at that point. And also to understand why this is happening, that the majority of the curves don't have a secondary wave if the mean generation time is small, we can see here that the blue curve is the one for varying infectiousness of mean generation time equal to 4. And we see that this blue curve stays at 0 for a longer time, let's say from 100 to more than 200 days. And so there are more opportunities to die out with respect, for example, to this green curve, which is the varying infectiousness of with mean generation time equal to 8. So this is why we think small mean generation time will have only 1% or a small percent of curves with the secondary peak. And so my conclusions are the following. Different combinations of infectiousness profile and infectious period have no impact on the critical vaccination VC as long as they lead to the same R naught. So the first conclusion is that we don't need actually the complication of Markovian models to compute the critical vaccination rate. But we need this non-Markovian model for the transient behavior, because the output of the non-Markovian have damped oscillation of higher amplitude than Markovian model. They are definitely much more pronounced in terms of these waves. Interestingly, the ABMs produce results close to the PD formulation with large population size, and with this approach of considering the mean generation time as an input and creating the infectiousness profile as a consequence from that through that equation I showed at the beginning. And the ABM suggests that ABMs or ABM simulations suggest that even with large population, epidemics could die out. That was the interesting thing after an initial peak, if the decline in prevalence is fast enough. So I hope you enjoyed this presentation, that the presentation was clear enough. Please tell Professor Xu Ling about any question you may have, and I will be happy to answer to those. Thank you.